Hi, this is Dane Quinn from the University of Akron, and for today's video lecture, I would like to focus on transmissibility. This really deals with the forces that are transmitted from a structure to the ground as it undergoes mechanical vibrations. Here's our example system, and we often start off with this. It's a spring mass damper system, mass M, stiffness K, damping B, and we're going to apply a force that's harmonic to this system, right? So F of t is F naught sine omega t. F naught, of course, is the amplitude, and omega is the frequency. We've looked at this problem before, and in that, we actually went through and found the steady state solution, or the particular solution in this case. So that looks like a harmonic function as well, with some amplitude, x, and then a phase shift relative to the forcing given by phi. Again, we've already solved this system, so we know how it responds, right? We can solve for x of t in steady state conditions, or again, the particular solution. What we're interested in now is what force is then transmitted to the ground. If there was no foundation, no elastic suspension here, in that case, whatever force is applied is directly transmitted to the ground. However, once we put an elastic foundation, then the forces that are actually transmitted through this spring damper combination are not necessarily the same as the applied load. So let's go and look at a free body diagram. That's where we always start when we talk about forces. Here again is the elastic foundation, right? Stiffness K for the spring, damping coefficient B for the damper. Let's go and identify the forces that act on this system. So here we'll represent this as Ft, right? And of course on this side we'd have minus Ft. So again, this is the force applied across this spring and damper, and as a result, this is the force that's actually applied to the ground as this system moves. So the force across the spring damper combination can be written as F of t, which again is a function of time, is some scalar quantity, in this case the I direction, where F of t, and again this is now the scalar amplitude, is equal to k times x plus b times x dot. Again, for the spring, the force is k times x, and for the damper, it's b times x dot. Since these are parallel, they just add together. And again, this is the force transmitted to the ground. Again, for this system, this F of t, this transmitted force, is not necessarily the same as F of t, the applied force, because really the force transmitted to the ground depends on the response of the system. Fortunately, I've already solved for the response, so I can use that information. I can use this amplitude and phase, and in particular this solution, to determine what's the force transmitted to the ground. So here it is again, right? This is the force transmitted to the ground, this is the response, and the amplitude and phase. So really what I want to do is just take this expression, right, with this amplitude and phase, and plug it in to determine the force transmitted to the ground. So let's do that. So here F of t is equal to k times x. Well, x here is amplitude sine omega t minus the phase shift, plus b times x dot. Well, so I have to take a derivative of this. That's okay, I can do that. X omega cosine omega t minus phi. So here, what I'd like to do is combine these two pieces. right? Because after all, I have a sine and a cosine. We know that we can actually put those together and write that as a single harmonic function with frequency omega and then a different phase shift, right? So here, when we do this, we end up finding that the amplitude is k squared plus b omega squared. And then I'll write that as a sine function. And so we have the argument of these two, which is sine omega t minus phi. And then we have an additional phase shift because, again, we have a sine and a cosine. So we'll call that phase shift, I don't know, let's call it psi. And here, psi is b omega divided by k, which it turns out that if you write this in terms of our sort of system parameters, it's 2 zeta omega over omega n, or 2 zeta r. So again, this phase shift is related to kind of the system, well, frequency, ratio, and natural frequency. So again, if you want to pause this and work this out, please do so. But now what I really want is to write this in terms of the applied load, right? So we'll take the amplitude and introduce it into this expression, right? So we have x, so this becomes f naught divided by k times, well, all of this stuff. Right, so on the bottom we have 1 minus r squared plus 2 zeta r quantity squared. We have a 1 on the top, and then square root of k squared plus b omega squared, and then sine omega t minus phi, again, plus this additional phase shift. Okay, so we can actually simplify this. Notice that I have square root of some k squareds here. Let's take this k in the denominator, factor it in, right? So we end up with a k squared, and this would be divided by k squared. Okay, so that simplifies to 1. And then we have here b omega over k, quantity squared. So maybe if you want to pause this and work out the algebra, that's great. But what we'll find is that we end up with a b omega over k, which is 2 zeta r. So this actually simplifies considerably. So we end up with f naught times this quantity. In the numerator, we have 1 from here plus 2 zeta r squared from here. And then we again have our denominator. 1 minus r squared, I'm missing a squared there, plus 2 zeta r quantity squared. And again, sine omega t minus phi plus that additional phase shift. So what we find is the amplitude of the force transmitted, right? So we'll represent that by f of t, right? These indicate amplitude of this function, is simply this quantity, f naught times, well, denominator 1 minus r squared, 2 zeta r, quantity squared. In the numerator, we have 1 plus 2 zeta r squared. This is known as the transmissibility. And it's abbreviated with a TR. And really what we see is that this transmissibility here is essentially the amplitude of the force transmitted divided by the amplitude of the applied load. So again, it has a physical interpretation. It's the ratio of the force transmitted to the applied force. I really want to look at that in some additional detail, right? So here again, we have the force transmitted is the applied load times the transmissibility. And again, this is the transmissibility that we identified previously, right? So once again, just to kind of emphasize this transmissibility, which is the amplitude of Ft divided by F naught, can be interpreted as the force transmitted to the ground divided by the applied force. So what do we want? Well, we'd like to go and understand how this changes as the natural frequency and damping ratio vary. So, for example, if zeta is equal to 0, then the transmissibility is, well, 1 divided by square root of 1 minus r squared, right? Or square root of 1 minus r squared and the absolute value of that, right? Remember, when I take a square of something and then take the square root, we always take that positive branch of the square root. So that's effectively the absolute value. Okay, so over on our plot, let's go and draw that in, right? So you can kind of see what this is going to look like. This is the transmissibility if zeta is equal to 0. Okay, well, as we increase zeta, right, I have a number of different curves that I've sketched out, right? So I'll go ahead and kind of fill those in. Let's see, let's do blue for the next curve. And this would be the curve for zeta is equal to 0.1. Let's use green for the next curve. Okay, so that comes up. Okay. These two are actually very close down here. Green is for zeta is equal to 0.2. Oh, let's do orange next. Orange is zeta is equal to 0.5. And then finally, if I increase zeta to 1, right, actually we get a curve that looks like this. Further increases to zeta, right, basically you can kind of see what's happening, right? Down here, this basically levels out, kind of shallows out down here as well. Now, one important thing to notice is that if r is equal to a certain value, then all of these points pass through the same spot. And that corresponds to TR is equal to 1. So if TR is equal to 1, right, let's go and figure out what that frequency ratio is. Here I'll just set the transmissibility equal to 1 and then solve for R. Well, I'm going to bring this denominator to the other side. I'll actually square both sides, right? So what I end up with is 1 minus r squared, quantity squared, plus 2 zeta r squared, and then equals the numerator over here, which is 1 plus 2 zeta r squared. Notice that these terms drop out. So the solution to this doesn't depend on zeta at all. Again, all of these curves will pass through this point regardless of the value of zeta. So what is the solution to this? Well, essentially, what we find is the absolute value of 1 minus r squared has to be equal to 1. So that implies two solutions, right? Because if 1 minus r squared is equal to 1, right, then I get r is equal to 0. Okay, that's actually this solution over here. the second solution would be 1 minus r squared equals minus 1. Again, the absolute value of that is 1. So that gives me a second solution. R is the square root of 2. And that's the solution that we have here. So the conclusion here is that at r is equal to the square root of 2, the transmissibility is equal to 1. Well, let's go back and think physically kind of what this means. The transmissibility is the ratio of the transmitted force to the applied force. So if TR is 1, then that means that the force transmitted to the ground is exactly the same as the applied force. However, if TR is greater than 1, that implies that Ft, the magnitude, is greater than F naught, the magnitude of the applied load. And if TR is less than 1, that means, well, the force transmitted is less than the applied load. So, looking at these results, we find that for R between 0 and the square root of 2, TR is greater than 1. So this corresponds to amplification. So that the force transmitted to the ground is actually larger than the force that's applied to the structure in the first place. However, for R greater than square root of 2, the transmissibility is less than 1. So here we would say that the force applied to the ground is attenuated relative to the force that is applied to the structure itself. Another important aspect of this is that as the damping increases, the transmissibility moves closer to 1, which again implies that the force transmitted is equal to the applied force. As R gets very large, the transmissibility goes to 0, but it does so much slower for increasing damping relative to the undamped system. Now let's see how we can use this idea of transmissibility in engineering design. Really, when a system is subject to a harmonic force, we can actually design that foundation, and in fact the whole system, the mass damping and the stiffness, to isolate that applied force from the ground. Again, thinking about the original problem, we had a harmonic force that was applied to our mass, and then we're asking what force is then transmitted to the ground. If we operate out in this region, then we've actually reduced the dynamic load applied to the ground as compared to the dynamic load applied to the system. So here we talk about this isolation in terms of percent isolation of the force. And the percent isolation is directly related to the transmissibility. In fact, it's 1 minus the transmissibility. So, for example, if I had a transmissibility of, say, 75%, right, so 0.75, then that means that I would isolate 25% of the force. So now, how do we design based around this? Well, we have a couple of different things that we typically do, right? Primarily, we look for a desired transmissibility at an operating condition, right? So we'll define this as, say, TR star. That's our design goal at operation. So if we have a system and it's being operated subject to a certain frequency, and let's say that is omega equals omega star, then I'd like to design the structure so that we obtain a specific transmissibility. In terms of our transmissibility plot, this design goal implies that the transmissibility lies at some specific value, which we have defined as TR star. Here again, we see that we can obtain that for a variety of different damping ratios that correspond to different frequency ratios. And looking back at our transmissibility, essentially we would have to satisfy the following. TR star is equal to, well, in the denominator, 1 minus R star squared 2 zeta R star squared. Then in the numerator, 1 plus this quantity. So again, solve for the frequency ratio. And so if we know the frequency ratio, then we can determine the desired natural frequency of the system. Because R star is our operating frequency divided by the natural frequency that we would design to, or the desired natural frequency of our structure would be the operating frequency divided by the target frequency ratio. So again, if the desired transmissibility is specified, we can determine the frequency ratio, and this is now a function of the damping ratio as well. Our second design goal is related to the maximum transmissibility as the forcing frequency varies. In this context, remember that R, the frequency ratio, is omega divided by omega n. Again, omega is the operating frequency, or square root of m times omega divided by the square root of k. So looking at the change in the transmissibility as omega varies is equivalent to looking at the transmissibility as the frequency ratio R changes. Again, in this case, we're interested in the maximum transmissibility as this operating speed varies. What we actually evaluate is the transmissibility at resonance. And remember that resonance occurs when the operating speed is equal to the natural frequency, or R is equal to 1. We'll define this value as TR1, again 1 indicating resonance, which is the transmissibility at R is equal to 1 as the damping ratio varies. Looking at our transmissibility plot, we might be interested in a value of TR1 as shown. Again, this value at resonance closely approximates the maximum transmissibility as the operating speed changes. So we can evaluate this, right? TR1, just put in R is equal to 1 in this expression, and we see that that reduces to 1 plus 2 zeta squared divided by square root of 2 zeta squared. Or we can simplify this a little bit as 1 plus 1 over 2 zeta squared. And now we can actually, given this transmissibility, TR1, we can solve for the damping ratio. So that the damping ratio is 1 divided by 2 TR1 squared minus 1. From a design perspective, why might we be interested in this quantity? Well, let's say we have a design goal. So we're operating our mechanical system at some frequency. You could think about a machine with a rotating component at some angular speed, which gives us our forcing frequency. Well, when we turn this machine on, it doesn't immediately rotate at our desired speed. Instead, right, it starts off at rest. So in order to get from rest to our operating speed, that angular speed of the machine begins to increase, which implies that R increases. So as we bring our system up to operating conditions, we actually would traverse this whole region of R. And you can kind of see what might happen. As our rotating speed passes through resonance, we can actually have a fairly large transmissibility. And as a result, we can have large vibrations being imposed to the supporting structure for our machine. Right? Again, this transmissibility could be high. Part of our design goal is to keep that transmissibility limited as we pass through resonance. Now, one interesting aspect of all this is that, in a sense, these two design goals are sort of competing. If we want to minimize the transmissibility at some operating speed, well, that implies that we want to be as low as possible out here. We see that that actually requires low damping. As the damping decreases, then the transmissibility for large values of R decreases. However, the transmissibility at resonance actually increases. Right? So we have these competing design goals. We want to choose the damping so that the transmissibility at resonance is low, but we also want the damping low enough so that a given transmissibility at our operating condition is not pushed out for R sufficiently large. Again, for design purposes, this value of R is related to the mass and the stiffness and the operating speed. So if the operating speed is set by the design requirements, then changing R, well, if we want to increase R, right, so that we reduce the transmissibility, we could increase the mass, or we can decrease the stiffness. Let's look at an example now. We'll take a machine of mass 100 kilograms and assume that it rests on a rigid support. Right? Essentially, it's just sitting on the ground and is subject to a harmonic force of amplitude F0 and frequency omega. What I'd like to do is redesign this support system. So instead of it sitting on the rigid ground, right, it sits on an elastic foundation. Spring stiffness K, damping coefficient C. And I'd like to design this so that when the operating frequency is 4 hertz, the system's 40% isolated. And at the resonance, the dynamic force transmitted to the ground is no more than twice the amplitude of the applied load. Right? So again, what I'd like to do is reduce the dynamic amplitude of the force transmitted to the ground, right, by 40%. And I'd like to make sure that as we pass through resonance, that dynamic load is not too large. Right? So in fact, no more than twice the amplitude of the applied load. Let's look at this second condition first. Well, that's our TR1. Right? So at resonance, TR1 is equal to 2, right? Because we want no more than twice the amplitude of the applied force. Well, using our results from the previous slide, here we'll basically go and solve for zeta. So doing so, zeta is 1 divided by 2 square root of 3, which is about 2.89. Now, our second condition is the transmissibility at the operating speed. Right? So again, we want our transmissibility at the operating condition, TR star, to be equal to 1 minus the percent isolation, which is 40%. Right? So 0.4, or we'd like the transmissibility to be 0.6. Right? So again, it's 60% of what it was originally. That's 40% isolation. So let's go back and look at our transmissibility at the operating speed. Remember that TR at R star and zeta, which was defined as TR star, is, well, in the numerator, 1 plus 2 zeta R star squared, and in the denominator, we end up with 1 minus R star squared squared plus 2 zeta r star. So again, this is known, right? It's 0.6. We've already found the damping ratio. So we need to solve for the frequency ratio. And I will remind you that the frequency ratio is square root of m times omega star divided by square root of k. So this frequency ratio depends on the system parameters, right? And in particular here, it depends on the stiffness that we're going to design to. So even though the excitation frequency is constant, the frequency ratio is a property of the system, right? It's one of these things. It depends on the foundation. So we need to solve this relationship for r star. Okay, well, let's simplify and write an equation for r star. I can basically square both sides. I'll take this denominator, I'll move it to the left, and this reduces to tr squared. And then again, we squared this denominator, put it over on the left. We get 1 minus r star squared plus 2 zeta r star squared. And then on the right, we're just left with the numerator. So that's 1 plus 2 zeta r star quantity squared. And again, this transmissibility is 0.6, and the damping ratio is given here. So if you notice, this is just a polynomial, right? In fact, it's technically a fourth order polynomial, and it reduces to 0.36 when I add in all these numbers. R star to the fourth minus 0.933 r star squared minus 0.64 equals 0. Okay, so the nice thing is this is actually quadratic in r star. So we can solve this. And this quadratic equation gives me two solutions. Right? One of those solutions is 3.1559. Again, I did all this algebra. And the second solution is minus 0.5633. Clearly, we're looking for this solution. If I were to take the square root of this, I'd have an imaginary frequency ratio, which doesn't really make a whole lot of sense. And we also know that the frequency ratio should end up being fairly large because the transmissibility is less than 1. Right? So finally, we can use this solution to go back and solve for, well, in this case, the stiffness. Before I do that, notice that omega star was given in hertz. Right? So it was 4 hertz. Well, I need that in radians per second. Right? So 4 hertz, 2 pi radians per cycle, that's 8 pi radians per second. Finally, r star squared here, again, is omega star divided by omega n squared, or m omega star over k. So we can solve for k, because this desired frequency ratio is 3.1559. We know the mass. I know the desired operating frequency. Right? So k is m omega squared divided by r squared. Or, plugging in these numbers, we get 2.002 times 10 to the fourth newtons per meter. Now, turning to the damping, we'll use the damping ratio. So remember, the damping ratio was defined as, here our coefficient is c, right? So c divided by 2 square root of km. I know the damping ratio, right? That was determined by the transmissibility at resonance. K I just found, m is part of the problem statement, so I can solve for c. Okay, so now c is 2 zeta square root of km. And using these values, we end up with C is 8.168 times 10 to the 2 newtons per meters per second. Right? Those are the right units for damping. So we've done it. Given these desired conditions, right, our design goals, we've found the stiffness and the damping, right, that meets these requirements. Finally, one additional thing that we can calculate, actually after all this, is, for example, the static displacement. That's sometimes useful. So notice that the static displacement in this case is the weight, mg, divided by the stiffness. Right? So we can also write this as g over omega n squared. Omega n squared is k over m. And we find that the static displacement for this problem is 0.049 meters. Okay? So roughly 5 centimeters. Again, we've used the transmissibility to ultimately design our foundation so that we get good performance for our system in terms of the force that is applied to the ground. Right? So we can actually reduce the dynamic load applied to the ground for a given excitation amplitude. Right, so that's it. That's our lecture on transmissibility. Again, once we know the response of the system, we can go back and determine lots of different things. And in particular here, we look at the force that is transmitted to the surrounding support structure. So that's it. Thanks so much. Always looking for feedback and comments. Please send me an email, right? Drop me a line. And I will talk to you again. Take care. Bye.